In Lab 3, we found the magnetic field of bar magnets, which have a permanent dipole. We wanted to measure the distance dependence of the magnetic field due to a bar magnet, which should be approximately 1 over r cubed, according to the Biot-Savart law. The Biot-Savart law is an equation that describes a magnetic field created by a current-carrying wire and allows you to calculate its strength at various points. Using it requires calculus, and you can derive the formula for the magnetic field of a dipole from integrating the original Biot-Savart law. The result indicates how the magnetic field of a dipole, regardless to whether it is on axis or not, is still proportional to 1 over r cubed in terms of distance from the dipole to the observation location. This shows the magnetic field will decrease with increasing distance by this factor. Materials needed for this lab were a bar magnet, a smartphone, a meter stick, tape, and the Excel spreadsheet provided to us by our professors. On the smartphone, it was required to download a special magnetometer app, such as Teslameter, to measure the magnetic field due to a permanent dipole magnet. The compass app that comes in the smartphone is not sufficient because compass apps usually use GPS tracking to calculate the geographical north instead of the magnetic north. They also sometimes filter out local magnetic fields, which would be a problem since what we're measuring is a local magnetic field of the bar magnet. To find the magnetometer chip in the phone, you had to slide the phone slowly along a line perpendicular to the meter stick, being careful not to rotate it. Where the absolute value of the x component is at a maximum and the y is at a minimum is one of the lines where the magnetometer sensor is along. Then you rotate it 90 degrees and move it again along the line perpendicular to the tape, this time looking for a maximum in the absolute value of the y component and a minimum in the x, and then you stick a piece of tape across that line. Then you can find the approximate patch where the sensor is. For the Excel sheet, we found the distance at which the sensor produces a magnetic field with an x component of 1,000 microteslas and made magnetic field measurements there, and then also at 1.5 times that distance and 1.75 times and 2 times that distance. We then plotted ln b and ln r to get a graph where the slope is n and the intercept is ln k, since the magnetic field B equals kr raised to the n. The experimental n value, which was the slope, was negative 2.5. The n value that should have been recorded was negative 3 due to the Biot-Savart law. We used a computer model to visualize the off-axis magnetic field. The expression shown here is very accurate at far distances from the dipole, but then less accurate up close. The computer model can help us visualize this expression. We are then also able to solve for mu and plug that into our computer model. We could compare the values calculated by the computer model to the value calculated by the phone app, which was done when the magnet was tilted at a 45-degree angle. The computed value and measured values are listed below. Computed was 88.4 in the x direction and 265.3 in the y direction, and measured was 90.3 in the x direction and 252.9 in the y direction. If I had not oriented my experiment to compensate for magnetic north, the results would have changed by being skewed, since the Earth's magnetic field would not have been canceled out or ignored, so the magnetometer would reflect that as well, causing the magnetic field measured to be incorrect for just the bar magnet. If I were to stick 2 identical magnets end to end and run the experiment again, then the measurements would differ by a stronger magnetic field being calculated, although it would not be twice as strong since one of the magnets would be a magnet length further away from the magnetometer than the first magnet. In conclusion, key physics principles demonstrated in the lab are magnetic fields, magnetic dipoles, and distance dependence. The results I achieved were close to the actual value of n, but human error could have contributed, and the fact that it is hard to eliminate all magnetic influences from around the lab site in order to just record the magnetic field of the bar magnet itself.